Hello, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm the host for today's session. And we do appreciate your attendance today. Before I hand this off to our guest presenters, as we are in the habit of doing, I'd like to run a few poll questions to get a sense of the audience focus and to introduce our subject with a little bit more heightened interest. So if you would please participate in our poll questions. The first is considering safety as a first priority. What do you consider the next predominant factor in choosing your arc flash mitigation? So let's see if we can gather some feedback. We frequently bring in associates in the industry on subjects that surround the area of safety. And this seemed like a very pertinent topic, especially when we get into the subject of arc flash safety. All right. And here's how people have weighed in on this. Good. Then the next question is, what percentage of the projects that are involving arc flash mitigation method do you review in detail with the clients prior to the design? So we have a couple of choices here as far as percentage of the time. And I'm curious to see how some of these results come in. It's not something that we discuss that frequently, so I appreciate the opportunity to see the feedback. All right, here's how folks have weighed in here. Interesting stuff. All right, thank you. And the last one is, does the industry provide sufficient information to make it easy to do your job? Yeah, we're getting quick answers on this one. It's just kind of what we suspected. So we're going to close out this poll question and share the results. And it looks like we're well suited for what we're about to see. So I appreciate everyone for participating. And now I'm going to hand off the presentation. So yes, let me hand this off to Jeff so he can make the presentation, the introductions. Excellent.
Thank you, Jim. So welcome, everybody. I appreciate you attending today. I'm one of two presenters today. My name is Jeff Miller, and I'm the manager of specifiers and channel programs at Schneider Electric. Basically, that means that I work on a lot of the programs and information and content that we try to help with consultant engineers, engineers within various firms, to get you the right information and tools that you need. And we manage it digitally, and as well as a lot of sales teams that work with specifiers directly. I have with me today Antony Parsons, a man much smarter than myself, and he is an expert on arc flash as well as many other things. And he has frequently contributed to IEEE and wrote a very interesting paper that's similar to this one, but I'd like to say this one's a little bit of an update, and I hope you guys will enjoy it. So roughly about 2,000 workers are injured every day due to electrical accidents. In addition to human safety concerns, we have commercial assets, business continuity, and legal exposure that can be adversely impacted by arc flash events. There are many causes of arc flash events, but and many ways to address them, but one of the biggest challenges is knowing what options are available to you. It can take some serious digging to learn these options and how to approach them in electrical designs. In this webinar, we're going to hope to provide you with the following learning objectives to help you tackle the many challenges associated with arc flash mitigation. And we hope that you'll enjoy it, but I'm sorry to say that we had to limit the scope of this discussion to a 1-hour webinar, but we hope you'll join us in the future on webinars that go into detail on this topic. We're trying to provide some overall guidance here, and we're going to discuss these additional webinars and getting access to some of the tools we'll talk about today towards the end of the webinar. Tony, take it away. Thank you.
All right, thank you, Jeff, and thank you, Jim, and for everybody joining us this afternoon or this morning, I guess, depending on where you are. Welcome. Yeah, like Jeff talked about, we're going to talk about arc flash mitigation, and those poll questions are always interesting. You know, they give you some insight. I would definitely like to see the percentage of folks who are reviewing safety requirements before detailed design move up from, you know, I think 0 to 25% was our most popular category there. I'm a big proponent of you know, looking at safety, including arc flash safety in the, you know, early on in the design process rather than kind of making it an afterthought. One of the issues may be, you know, related to that last poll question. The industry, you know, we kind of got a mixed report card on whether or not we make it easy to try to parse through the different solutions that are out there. And hopefully, you know, some of this information that we start sharing today can help kind of close the gap on that a little bit. But, you know, arc flash analysis and mitigation, you know, you guys don't need me to tell you that the industry has made great strides in recent years in terms of arc flash analysis methodologies, standards that give us better ideas on safe work practices to use. But you know, for all the good things that we've done, those are really only part of the story. You know, to go beyond, we know that several end users go to the, you know, once they have a study done, once they have some work practices in place, would like to go further and look at ways to actually mitigate the hazards in the system, reduce the risk that their workers may face. NFPA 70E gives us guidance on several different mitigation methods that can be used, including engineering controls. And at least my explanation of what an engineering control is that it's a product or design technique that can be used to help engineer the hazard out of the system. And that's great. That's another area where there's been a great deal of interest and activity over the past, you know, decade and a half. There are a number of innovative solutions out there from all different manufacturers on, you know, ways that arc flash events can be cleared more quickly or workers can be protected in some way, to the point where it becomes difficult to choose what you should use. You know, it's not an easy consideration in many cases, especially when you look at the ideas that, you know, and each of these things that I've got here, we're going to go into a little bit more detail as we continue to go through this. Some of the solutions out there may be task specific. So you really have to think through, okay, what are the workers in my facility doing or in the facility that I'm doing a design for? What are they actually engaged in that may expose them to arc flash hazards, so that we can make sure to, you know, kind of address those things. We need to look at what the solutions actually do. We'll talk about how some address, you know, likelihood of occurrence of an arc flash event. Others may address the severity, but they rarely affect both equally. And so we need to understand what they do, what they don't do. All mitigation solutions, bottom line, are not created equal. So how do we choose between them? What we're going to do, I'm going to give you some big picture stuff first. I'm going to pass it back over to Jeff. He'll talk about some specifics on a guide to mitigation that we're putting together, and then we'll kind of close out looking at some details on some of the popular solutions that are out there. The first thing that we're going to do is look at different categories of arc flash mitigation methods. Now, our contention with this is going to be that pretty much any arc flash mitigation solution that you can think of, any engineering control anyway, can be put into one of 4 different categories. And we'll talk in more details about these in the following slides. But, you know, avoidance solutions help you avoid the hazard. Prevention solutions stop the arc flash events from occurring in the first place. Containment, and then reduction, trying to actually reduce the energy. As far as I'm concerned, you know, really the first step in trying to understand what solutions are effective in a given facility or in a given situation comes with understanding what the solutions in these different categories do. We'll talk about some examples of each of these, and there are some common characteristics that come to play that really help us understand, you know, again, what they do, and in some cases, almost as importantly, what they don't do, so that again we can work towards picking the things that we need to in order to achieve our safety goals. So let's look at these, each of these briefly. First category is what we're calling prevention solutions. Solutions that make arcing faults less likely to occur in the first place, because you know, it's a no-brainer, I guess. The easiest arc flash event to deal with is the one that never happens. And there are a lot of ways that we can try to reduce the risk that an arc flash occurs in the first place. We're starting to see more and more innovations in this area. But sometimes it's as simple as putting additional barriers or compartmentalization in equipment. Maybe making it harder to drop a tool into energized bus or something like that. Sometimes it may be using insulated bus, including solid insulated switchgear, gas insulated switchgear. Air insulated switchgear is fine. It's been around for a long time, but may not offer you some of the protections that some of these other alternative methods do. Even things as simple as high resistance grounding can be a potential prevention method. High resistance grounding, the idea being that you significantly limit the energy that's available in a single line to ground fault. If you only have 5 amps flowing, if you have a ground fault, then it's much less likely to escalate into a 3-phase fault that could be a much more explosive event. It brings up, though, one thing that's kind of interesting about these prevention solutions. I say down there below, these solutions tend to primarily affect the likelihood of occurrence, right? So if you can take single line to ground faults to some extent, at least out of the equation, then yeah, you've reduced the risk that doing something or making a mistake inside a piece of equipment is going to create an explosive arc flash event. You may not, just by virtue of the high resistance grounding system, eliminate the probability altogether. Because even on a HRG system, you can still have a phase-to-phase fault or a 3-phase fault that would burn just as brightly as it would if it was solidly grounded. And so there's one of the challenges. Certainly, reducing that risk is a worthy goal. It's a significant benefit potentially to the workers around that equipment. It can be difficult to quantify this, at least in some ways. How we reduce the risk. How much do we reduce the risk? Do we change the PPE that we're using, et cetera? But prevention solutions, I think we've seen a move toward this. There's been several innovations kind of in this area introduced within the last few years, and I think this is going to continue in the industry. But we can't prevent all arc flash events, so maybe we want to look at solutions that reduce the energy when they do occur. And so next category, reduction solutions that clear arcs more quickly in order to reduce the available incident energy. And this works because of that second bullet there. Incident energy is directly proportional to time. Now, if you've spent time looking in IEEE 1584 and seeing the equations that are in there, they're very complex and very involved. But one thing is very simple. Again, it's directly proportional to time. If you change your clearing time from 1 second to half a second, for example, you reduce the available incident energy that could result from a fault at that location in the system. You cut it in half. Simple enough. And so if we can use fast-acting circuit breakers, if we can use fast-acting relays, fuses, whatever it may be, we can help reduce those energy levels. Arc flash maintenance switches may help us reduce the clearing time and reduce the energy when we might have problems otherwise maintaining coordination in the system. Optical sensing relays and other innovations are new ways to help detect and clear faults more quickly, but sometimes we don't have to use the new technology to get there. Sometimes reducing arc flash levels is as simple as making sure we correctly consider arc flash incident energy levels when we're doing coordination studies. That's what I mean by setting optimization. I continue to be surprised how many times I see studies that have been done either by colleagues or by others in the industry where really it seems apparent that the folks doing the study really don't understand the full capabilities of the protective relays or other devices that they're dealing with, and are just missing an opportunity, almost a free opportunity, to reduce incident energy in their system. So it's very important to perform the correct kind of studies and optimize those settings. The last bullet there is kind of unlike the prevention solutions, which you said would affect likelihood of occurrence. These tend to affect the severity of the event. We can reduce the calories, but if we're in maintenance mode off versus maintenance mode on, if you're in there in a motor control center bucket taking voltage measurements, no more or less likely to create an arc flash event. So again, kind of two aspects of risk there. Solutions may affect those differently. The third category is what we'll call avoidance solutions, solutions that help us remove workers from the vicinity of the hazard or help eliminate exposure, at least to some extent. And it works in a couple of ways. Incident energy drops off pretty quickly as you increase the working distance. So if we can, operate a breaker from a remote panel, or some kind of SCADA system, or even Bluetooth over over your cell phone, we can do that from a distance and be experience much less exposure than if you have to be standing right in front of the equipment pushing a button or whatever. Ideally, we find solutions that allow for tasks to be done outside the arc flash boundary. And that that picture that I have kind of on the top here, where we've got a guy doing thermographic scan through an infrared window, is a good example of this. Traditionally, to do the infrared scans, you're pulling covers off of energized equipment exposed to the live bus inside the gear. Well, if all you have to do is flip up a little cover on a window, you don't remove the cover, you don't open up the gear, you're not exposed anymore. You're kind of by definition outside the arc flash boundary in that case. And so there are many examples of solutions that fall into this category: remote operation, remote racking of circuit breakers. If you haven't seen it, go to the search engine of your choice when we're done and search for arc flash racking breaker, and you'll see what can go wrong in those cases. Certainly much better to be able to do that from the end of some kind of control pendant than when you're standing right in front of the gear turning the crank to get the breaker to go in. Infrared windows, or I guess even the more modern equivalent thermal sensors that can be embedded in the gear, partial discharge sensors. There are a lot of things out there that continue to be kind of developed and worked on that can help us do some of the maintenance tasks that we'd like to do while reducing the potential exposure of the worker. So these are great. They may reduce both the likelihood and severity to the worker. One thing to notice, and again, we'll come back to this more in just a few minutes, the hazard level at the gear itself is unaffected. We may not be able to change that incident energy level that we put on the arc flash label on the equipment, or the the value that you calculate in your EasyPower software, but we may functionally reduce the risk to the worker based on the tasks that they're doing. And there's one last note there at the bottom. These solutions do tend to be task specific, for better or worse. And what I mean by that, again, going back to that infrared scan, if you're the guy there with the infrared camera, that's great. It has removed the hazard for you. Doesn't do much for the next guy that comes in and has to rack the breaker back in. We'd be looking for a different type of avoidance solution in that case. Containment solutions, the last category, solutions that contain or redirect the arcing fault and its byproducts. And basically what we're talking about here is arc resistant switchgear. The intent is that the switchgear itself protects the worker who's standing adjacent to the equipment, reduces the severity, at least that the worker's exposed to. Likelihood is probably unaffected. It's kind of like the reduction solutions. I mean, if you're racking a breaker in or out on this arc resistant gear, at least from what I understand about it, you're probably not any more or less likely to create an arcing fault. The benefit, though, is if it does happen, the gear is designed to contain that and to protect you. Unfortunately, though, no protection for the equipment itself. Also, I'll say no benefit for intentional exposures. What do I mean by that? One example would be when you're doing voltage testing to verify that the equipment is dead during part of a lockout tagout procedure. Most of the time, that means opening a compartment or removing a cover in order to get access to do that testing. When you do that on arc resistant gear, it's not arc resistant anymore. And so, we may have to consider that, again, considering the tasks that you're looking on. Product ratings, you may not get protection for equipment applied outside of its ratings. That's true for any equipment, especially true of arc resistant equipment. And the main issue that I've seen with this, or area for misunderstanding, is understanding about the maximum arcing duration for low voltage arc resistant switchgear. Half a second is the typical value in the industry. If you've got a study done and EasyPower says you've got 60 calories at your main low voltage switchgear, guess what? The reason that you're there at that kind of incident energy level is because you have a clearing time of greater than half a second. And so you're going to have to do mitigation at that location before you can successfully apply arc resistant switchgear, something that gets kind of lost in the shuffle sometimes as we look at that. But in the right situation, very effective solution that can be used either by itself or in conjunction with some of these other things that we talked about. So that's great. There's our 4 categories. Again, we talked about some highlights and some examples from each of those. Technology is a wonderful thing, but developing an effective mitigation strategy means that we got to go beyond just understanding kind of where the different solutions fit into these categories. And what I'm going to show you next is a series of questions that we've come up with, really based on years of looking at these kind of problems with customers in different market segments, different industries. We've developed kind of a series of guiding questions to help sort through all the options. First thing that we're going to do is look at the questions and then get an idea of some of the solutions that are out there. But let's get in here and start looking at how we take what we've learned in those solution categories and start developing a strategy then for arc flash mitigation. Question number one, and in my mind the most important one, is fairly simple. What does safety mean to you? And what I mean by this, if we're going to mitigate arc flash hazards in a system, that implies that we've got some kind of problem that we're trying to solve, right? Arc flash levels are too high. We want to bring them down. We want to minimize the exposure. Well, what's our end goal? Anytime I have someone coming to me and say, hey, we've had a study done, some of the levels are higher than we'd like them to be. We want you to help us reduce the arc flash levels in our facility. This is my first question. And I'm surprised, to be honest with you, how many times folks have not thought through the answer to this question, because there are a lot of different possible answers, right? One answer is that, okay, we just want a system that will comply with NEC requirements. And there are some NEC requirements around arc flash mitigation. Article 240.87, for example, that says you apply arc energy reduction methods if you have low voltage circuit breaker 1200 amps or larger. Okay, we can do that, maybe without addressing things farther down in the system. But that's not the only kind of answer that we've gotten to this. Sometimes customers want to make sure we don't have any incident energy locations above 40 calories per centimeter squared. You don't want it to say extreme danger on your labels or in your study or whatever, right? So let's bring it below 40. Or maybe we want to bring it below 8 calories so we don't have to wear the full-blown arc flash suit. We've had some that say we want all incident energy levels, or at least anywhere that we can get them, to be less than 1.2 calories per centimeter squared. I will tell you, and if you looked into this in any detail, you know that this is true. The solutions that you need to get below 1.2 may be very different than what you need to get you below 40 calories per centimeter squared. To get you below 40, maybe all that you have to do is that setting optimization that we talked about, just intelligent selection of those settings. 1.2 is a different animal. So goals drive solutions, right? The optimal solution for each of these criteria that we have may be different. How can you solve a problem if you can't define what your goals are? I think the answer, at least from my standpoint, is you really can't. So that's why I say your first step ought to be to define a set of safety-related performance requirements. Once you got that, at least you know what you're aiming for, and that can help you start to kind of whittle the list down a little bit of solutions that might work for you. Question number two is kind of built onto that. Where or when is the exposure? How do you prioritize mitigation actions? And this comes into play, especially when you're talking about existing facilities. There may be limitations on the budget that you had to correct the problems, or available downtime to put in solutions. But you think about this: where do we start? All right, one answer is, well, we'll start with the highest incident energy level and then kind of work our way down. But it may not always make the most sense. I had, again, another customer that we worked with had a study done, and they said they were looking for some assistance in kind of developing strategies to deal with the arc flash hazard levels that that study revealed. Some of the substations, this was a large paper mill. Some of the substations in there had energy level of 60, 70 calories, something like that. I was saying, okay, well, we'll start here and we'll kind of work our way down. I said, no, we want to look at the MCCs, low voltage MCCs. Like, well, why? I mean, this is like 10 calories, this is 12. Well, the deal was, at those substations, they only interacted with those on an infrequent basis. When they're doing their annual maintenance, or very rarely did they have to do any kind of interaction with that, with that particular equipment. But the way the engineer at the plant explained it to me was, at the MCCs, they've got people in there on a weekly basis or even a daily basis having to reset, reset a motor or do some troubleshooting in an MCC bucket or whatever. The exposure was much more frequent in those locations. So even though the energy levels were lower, at least in their mind, if they could reduce the energy levels there from where they were, even though they weren't quite as bad as they were at some other locations, that gave them really more bang for your buck, if you will. They would have more immediate benefit out of that by protecting the locations where exposure was most frequent. Then once we got those done, we kind of moved on to those other locations. Another example, I said, when is the exposure? In some facilities, doing the infrared scans may be the most common task that would expose workers to hazards. Well, there's a case where it might lead you to one of those avoidance solutions that we talked about if reduction of incident energy was too hard. Maybe instead of having to replace circuit breakers to get something that can operate more quickly, or adding relays or whatever, maybe you just put in those infrared windows or those thermal sensors. You eliminate the exposure on the task that is really causing you the biggest problem, and kind of move on that way. So considering both the frequency of exposure and the specific work task can help you sort out the solutions as well. Question number 3, how do you evaluate likelihood of occurrence versus severity? And we talked about this with some of those solution categories. Some would reduce the chance that an arc flash could occur. Others would reduce the calorie per centimeter squared level. Not all of the solutions, or typically the solutions don't affect both at the same time, or at least to the same degree. Now, another thing I've seen, based on my own experience, a lot of folks look at different solutions and they think, okay, if I can't bring the number down on my arc flash level, if I can't bring the calories per centimeter squared down, then this is not a solution that I want to pursue. I don't think that's a really valid way to look at this, or at least it's not the ideal way. There may be cases like we just talked about with the infrared scanning. When is it okay to forget about bringing the numbers down and look at remote operation, look at thermal sensors, look at whatever else, in order to kind of functionally eliminate the risk to the workers, and continue to allow those energy levels to be a little bit higher. Just again, something to think about. How are we going to look at likelihood versus severity? Question number 4 kind of gives us a different twist on it. What about equipment survivability? And this is where we may be out on thin ice a little bit. It's at least difficult to quantify this. Even as somebody who works for an equipment manufacturer, if you came to me and said, well, I want to make sure if I have an arc flash at my switchboard, I want to be able to get that back up and running, the same day, rather than having to take 2 weeks to get these parts fabricated or whatever. So what energy level do I need to bring it down to? I have no idea. The industry as a whole has no idea. We've not done extensive testing to say, if you're below 8 calories, you're going to be back up and running in an hour. If you're between 8 and 16, it's going to take you a day. Above that, you got to replace the equipment. We just don't know. Common sense, though, tells you that if you've got a 4 calorie per centimeter squared event, it's going to be a lot easier to recover from than a 40 calorie event. And so in some cases, we've had discussions with folks that were in, I guess, high availability type facilities, critical data centers, hospitals, and this thing becomes, or this kind of criteria, equipment damage becomes part of the consideration as well. And so that can lead you to, maybe target lower energy levels than just getting it below, getting it below 40. If we get it to 39.8, maybe we're not happy if this is one of our major drivers. It could also drive you away from things like maintenance switches. What state is the maintenance switch in 99% of the time? Maintenance mode is off. You're not protected. Maintenance mode is on only when somebody's actually doing work on the gear. And so most of the time, you wouldn't get the benefit of potential additional equipment protection as well. And it's kind of it's a tough one to look at. I think this is one that you don't necessarily make this the number one factor in your arc flash mitigation strategy, right? Because nobody wants equipment damage. And if you say, well, I got to have an always on solution. I mean, there's a reason arc flash maintenance switches are popular. They help us deal with some problems that would be hard to deal with otherwise. And so, if you make sure, I guess, when you're when you're looking at your questions, looking at your criteria, that you don't kind of engineer yourself out of some solutions that would otherwise be very applicable in a real system. And then the last question, what are the other limiting factors or red flags? And admittedly, this is kind of a catch-all here, but what's our budget for these solutions? Maybe you're trying to get to 1.2 calories on a 40-calorie budget, or something like that. Generally speaking, the lower you try to go, or the more restrictive you are in your performance requirements, the more expensive things are going to be. You're going to have to put more technology in, or more advanced technology, to try to get those energy levels down. In existing facilities, what kind of downtime do you have to put these solutions in? Do they have any effect on reliability? Selective coordination, for example. What about equipment footprint? That can be an issue if you're looking at arc resistant gear. How do you vent the fumes or whatever? Equipment maintainability. Is there something upstream to trip? We put in an optical relaying system to protect the main breaker section in a low voltage switchboard. Well, you can't protect that low voltage main section by tripping the main of that switchboard. We need to trip something farther upstream. We've seen systems specified where there was nothing upstream to trip. So it really, kind of defeats the purpose of spending the money to put that in. Is there a reliable source of control power for that new advanced relay that you want to put in? And then the last one, last but not least, who's going to program, test, and commission the fancy relay system that you want to use? And I can tell you stories about, for example, the optical arc flash systems where the person that programmed the logic in the relays didn't actually have the optical sensors programmed to trip anything. So, instead of providing protection, really that relay was providing some degree of a false sense of security. And so, a lot of things have to come together in order to make some of these things work. So just make sure that we're considering these as well. And with that, we've gotten through the questions. I'll turn it over to Jeff here for a few minutes to talk a little bit about the guide before I kind of bring you home. Jeff?
Thanks, Tony. So I want to give everybody a warning at this point in the presentation that if you haven't already, and you may want to get your print screen and/or phones out to take pictures of the screen for the next couple slides, this presentation will be available on EasyPower's website once they make the video available for on-demand viewing. And we will have other ways to get a hold of these tools talked about at the end of the webinar. But I know how some people like to do that, so I'm giving that warning. Our customers came to us and looked at ours as well as our competitors' solutions for arc flash, and there's so many, and they just had questions, and it gets kind of complicated. Not just the questions that Tony answered, but then understanding all these solutions in detail and how they vary from each other. This guide that we created is pretty agnostic, and not only that, it's at a very high level to help with conversations about this. I think you're still going to need to go and do the legwork to dig into the details of the specific solution that you're looking at. But I think this really helps point you from what your goals are to what solutions you should be looking at. Not all the solutions are available for every application, so you also have to think about that. And what we did in this guide is, one, kind of talk about the different categories that Tony's already mentioned. Two, list the different mitigation solutions under each category. And then three, kind of talk about when they can be applied in very high-level terms and what the pros and cons are. So I'm not going to go in detail about all these. I'm just going to talk about things while giving you a chance to look at it. I do want to mention that some of the things that Tony's mentioned before, a lot of us are aware of the standards and the calculations we have to do around arc flash. And Tony's mentioned this, but we really don't address recovery time, costs, likelihood in those standards. So, and solutions themselves, when are they applicable and all that. So we put together this nice little chart. Tony will go through more specifically what each of these columns means specifically. But I think this gives you a good understanding of being able to compare this and the notes that go along with this of how to narrow down what you want to choose for your solutions and investigate. So here you can see prevention. A lot of these, again, have to deal with likelihood, and I think this is a thing that's really ignored in the industry. You know, we talk about things like lowering the energy, but you can't really quantify likelihood. So it's hard to convince our customers to say, well, you should do this as a solution. And they go, well, am I going to be able to work with this protective gear, or will how much is going to cost me, or why would I do this? And you say, well, the likelihood's a lot less. And they're like, what does that mean? So I think it's a very important way to mitigate arc flash, and I think it's very underserved in our designs. So here's an example, because we don't have a whole bunch of ones listed against this. And I do want to say, as people look through these, I think we mentioned at the very beginning, a lot of these are not under one category. They kind of, it's a blurred line between different categories. Obviously, arc-resistant gear is very popular. I was a consultant engineer for more years than I was working for a manufacturer. I had many customers just come to me and say, I want arc-resistant gear. One of these was for a critical facility that if they had downtime, they were down, and it cost them, I think, around $685,000 per hour. Of course, that's 10 years ago money. But they wanted arc-resistant gear. We talked about other solutions that would help them return the operation, but they're like, we standardize on this, we're doing that. And they didn't really even consider what might be best for them. So again, I love selling arc-resistant gear. It has its place, but you really need to consider all the solutions. And that's where in this guide, besides giving the tables, we give these little application notes. Here's probably the most popular way, reduction. Again, I'll give you time to take a look at these. I suggest doing a screen print and or, like I said, taking a picture with your phone and reviewing them in detail. I do want to mention a couple things. A lot of these technologies differ slightly between manufacturers, and the pros and cons may change. And I realize that, in this 1 hour presentation venue, we really can't go into the detail of all these. We're going to hit a couple of them. But we will be doing a webinar in the future where we're going to go into the detail of each one of these. And Tony's going to hit at least 3 or 4 in this webinar to kind of give you an idea of what we'd be looking at when we're looking at these solutions. As you can see, cost doesn't always equate to effectiveness, whether it's for safety or recovery time or impact. So I think it does a great service to the industry that we compare all the different advantages and disadvantages to a solution and pick the right ones. Before Tony goes on, I do hope everybody can stay a little bit. We're going to have questions at the end of the webinar. I'll look through the ones that are submitted. So if you have questions that haven't been answered so far or during this, please put them in the Q&A, and I'll ask Tony at the end of the webinar. Thank you. Take it away, Tony.
Okay, thanks, Jeff. Yeah, and this remaining part, we may breeze through a couple of things here. I want to make sure that we do have plenty of time for Q&A. But you saw kind of a preview of the guide that we've been working on putting together. Some of the parameters, are we getting protection during normal operation? Operation, opening or closing of a circuit breaker or switch, for example. Are we getting protection during maintenance or abnormal operation? The answer to that can vary. And so we try to assess that to some extent. Is this a solution that will reduce incident energy? And we talked about how not all the mitigation techniques do that. We're also trying to give you some guidance on if it does reduce incident energy, approximately how much. And this is not, these are not values that you can quote us on, so to speak. But at least it gives you some rough idea. Are we talking about 8-calorie range or less than 40 range or less than 1.2? Where are we coming in? Recovery time, we've talked about that, and this is just kind of a it's kind of a guess. It's kind of based on energy levels and based on some of the other parameters that we that we think we have at least some kind of answer on. but at least, it gives us, are we talking about longer recovery time, less recovery time? What about equipment footprint? What about impact on commissioning, the complexity or the time? Is this a solution that's available for retrofit? Most of them are, but not all. There is no field modification kit to upgrade your conventional switchgear to arc resistant, for example. And then the cost. What about install cost, the CapEx cost? What about continued operation or maintenance cost? We try to address those again, at least to some extent or in a relative fashion as we look at those. And so some of the specific solutions, I've picked a few of the popular reduction solutions to kind of look at. One example here is zone selective interlocking, just to give you an idea of kind of the guidance shown. ZSI, of course, is a system where you have communications wiring between different levels of protected devices, either circuit breaker trip units or protective relays. And the idea being that if you have a device that's not seeing a restraint signal from something downstream, you trip very quickly, trip with no intentional delay, trip instantaneously, however you want to put it. And so that could help you reduce clearing time in some instances. So we give you, some ideas up at the top. That's the row from the matrix in the guide. How much instant energy reduction are you getting? How much impact on commissioning is this going to have? This time we say it's medium, because if you want to fully test out the ZSI system, it's more involved than just secondary injection testing or a breaker that's in a standalone application. Adds a little bit to the cost. But then Jeff talked about those application notes. For example, typical configuration may leave some holes in the protection. Typical configuration where you have mains and feeders interlocked, you're really not getting ZSI protection on the load side of a feeder breaker. So something to consider, as you look at this. The maintenance switch, again, maybe one of the most popular, if not the most popular reduction solution. We're saying protection during operation and maintenance is both limited. Why is it limited? The idea there, you're getting protection for downstream equipment. And I've seen people who firmly believe that, okay, I've got this feeder breaker here in this switchboard. If I turn the maintenance switch on, now I can do whatever I need to. I can rack this breaker out or do whatever, and I'm protected there. No, you're protected downstream. You got to understand where that protection actually is. Impact on commissioning for this one, fairly low. I mean, maybe you're doing tests with it, maintenance mode off, maintenance mode on, to make sure the switch is actually doing something, but doesn't add too much to the complexity. Where we are saying, our application notes, you may have impacts on coordination when enabled for maintenance. And really, I've always said, if you turn maintenance mode on and you don't mess up coordination, you didn't need a maintenance switch. And so it's something to think about, right? How critical is the selectivity on that circuit? Do you have workers in the facility who are going to remember to turn the maintenance mode back off when they're done doing whatever they need to do? Optical sensing, we're giving some guidance on energy reduction, reduced instant energy. Notice here it says less than 8 calorie, 12 calorie range. Why is it not any lower than that? Because these optical arc flash sensing devices operate very quickly. The relays, typically they may send a trip signal in as little as 2 milliseconds after an arcing fault occurs. Well, the problem is you still have to trip a circuit breaker. And so you've got, 3 cycles or more that you wait for that to happen. That's why in one of our application notes, we say it may not provide much incremental benefit in some situations. We need to look not just at the relay, but what does it have to connect up to in order to make, to clear the fault from the system. Impact on commissioning is more, we've, again, some of the things that we've already talked about. Differential protection. I'm going to skip past that one to get to a couple more here and leave us some time. Digital multifunction relays. This is an example of one where it's a relatively low incremental cost, right? If you're laying out a medium voltage system, you're going to have protective relays in there of some sort, or at least if you're using circuit breaker protection. And so make sure that you're specifying relays that give you enough flexibility in order to get those levels down where you want them to go. I guess probably not too many people are using traditional electromechanical relays, single function overcurrent electromechanical relays right out of the box or right from the beginning these days anymore. But some of the simpler digital relays essentially have the same functionality that those did. But if you step up to just the next, kind of the next level, relays that have multiple overcurrent elements, you may be able to really kind of tailor your protection curves to get the kind of protection that you want. And the effectiveness may depend on the system topology, but the capabilities of these relays also give you flexibility in terms of you can use sometimes arc flash maintenance switches with these other kind of combining solutions. But even by itself, just the digital multifunction relay may get you well below that 40 calorie per centimeter squared threshold if that's what you're aiming for. So just make sure that you're not using things that are so simple that you miss out on some of the flexibility that you can get with a little bit more advanced solution. Current limiting circuit breakers or fuses certainly very great or very good for systems with high levels of fault current available. The last one, circuit breakers with instantaneous overrides below the arcing fault current in the system. This is one of the solutions that is listed in NEC 240.87, so we kind of addressed that. Less costly but more complicated than an ERMS switch or maintenance switch. Why do we say it's more complicated? Well, the maintenance switch is one of those things that it's almost a no-brainer, right? You turn it on, maybe you're dropping your instantaneous trip down to a minimum level. We know that's going to give us pretty good protection. With this, we're actually having to do an arc flash study. We're having to look at different system operating configurations to make sure that we get that trip level in below the available arcing current. And that may cause some problems with coordination, either upstream or downstream. It could, it's something that requires a little more thoughtful study to make sure we get it applied correctly. But if you can, very low cost compared to some of the other solutions, and can be very effective. If you have a breaker that's tripping instantaneously, at least in the low voltage world, you can't make a breaker trip faster than instantaneous. So we've got pretty good protection there if the system layout and coordination allows us to do it. And with that, summary, just real quickly, it's rare that any one arc flash solution fits every situation. We believe that understanding the characteristics of the various solution types is critical. What do they do? And again, what do they not do? Asking the right questions can also help guide you to those optimal solutions with, again, my opinion, the number one key, what is your performance requirement? And again, Jeff mentioned that the mitigation guide that we're working on, I'm sure we can get information on links or whatever to that as that does become available. And I think with that gets us through our presentation material. So Jeff, what do you have queued up in terms of questions?
Thanks, Tony. And like I said, anybody who has a question, please submit it in the Q&A. In the time that we have, we'll try to answer. We will, right after the Q&A, go through a couple links of where the information will be provided. And I'll try to also put them in the chat, so if you are able to stick around the webinar. The first question I'd like to ask is, what are the top 3 arc flash mitigation types that you see currently in the industry from your experience, the top ones?
The top in terms of popularity, probably number 1 is arc flash mitigation arc flash maintenance switches. I think, and I don't know where it goes from there. To be honest with you, we see, that is kind of most people's default thing. Oh, we've got a breaker 1200 amps or larger. We need to put in a maintenance switch. But the optical sensing is gaining popularity. It really, I guess it depends on system type, and depends on some of these other factors that come in. In terms of most effective, I'm a big fan, at least if you're talking about a system where you've got medium voltage distribution, transformer differential relaying, and using that in places where we wouldn't or might not have in the past. Transformer differential relays give you great protection if you're inside the transformer differential zone, but then you've also got primary, typically with the modern relays, primary and secondary overcurrent elements that can be, you can even combine them with maintenance switches. You can do a lot with one of those, kind of our modern day transformer differential relays.
Thanks, Tony. I'm actually going to answer this one myself. Someone had asked, had they seen, I'm going to reword this a little bit, likelihood affect whether OSHA gives a fine or not if a accident happens. So obviously, if an accident happens, you're going to be looked at for your safety programs and what you've designed and everything like that to see what your, what your exposure is there. But again, if the issue with likelihood is you wouldn't have an accident in the first place because the likelihood is less. One of the other questions here are, what are the differences in arc flash mitigation for medium voltage switchgear versus low voltage switchgear? Okay.
Yeah, good question. I think in a lot of cases the solutions are similar. With medium voltage gear, you don't have built-in instantaneous trip units or whatever that that may be on the breakers themselves. You're talking about external protective relays, but still, many of the same functions or the same functionalities can be used on those medium voltage devices as with the low voltage. You can do arc flash maintenance switches just as well with a digital relay as you can with a low voltage breaker trip unit. All the manufacturers that have these, the relays have enough logic built in. You wire up a switch to a digital input, you can get that done. We probably may see more use of optical sensing at medium voltage. You probably see more differential protection at medium voltage. In particular, bus differential, that can be a little bit problematic at low voltage just because of space to mount CTs. But yeah, I mean, I guess I mentioned a couple of differences there, and we probably, arc resistant is probably more popular at medium voltage than low voltage as well. But I don't know that there's really two different sets of solutions. It's just that, kind of the nature of those systems may mean that you may be looking at a little bit different mix of what's typically used.
The calculated fault currents are usually different than actual operating fault current. Can relays detect actual operating fault current and display the actual arc fault levels?
I would think so. I mean, again, those digital relays, typically they're going to have enough intelligence built in to you can set those up to capture event reports when they happen, and typically as part of the event report, you're going to get maybe traces of the current, or at least readings of the maximum current. So yeah, I mean, typically you would expect your relays to be able to give you a sense of that.
Okay. Oh, this one's a hard question then to answer.
Uh-oh.
How often does OSHA audit companies for arc flash compliance, and what's involved? I know if they have an accident, they're likely to get audited. But Tony?
Yeah, and I will preface this by saying I am no OSHA expert, and I don't try to keep up with what they're doing around enforcement activities. Usually, just don't have the bandwidth necessarily to try to keep up with that. But at least from what I've understood or what I've heard on it, I'm not aware of cases where they've been kind of dropping in, doing surprise inspections and looking to audit your PPE or whatever. But like Jeff said, if there is an accident, you can be assured that they're going to get involved and look at it. So if I don't know if anybody has any information other than I do, but from what I've understood, they're doing this, but not necessarily doing it in a proactive manner, if you will. It's more after the fact when they're doing incident investigations.
Yeah, I will say I was also a contractor in my past life, and if you have disgruntled employees, they have a habit of calling OSHA on you. So
there you go.
Make your workers' employees happy.
yeah, there you go. But again, they're kind of acting on some kind of information, right? So it's keep
Rarely is it a random. I do know the really large contractors and are called upon every once in a while. Usually the very large ones. Besides that, inspections are somewhat rare unless somebody calls. Okay, I don't know if we can answer this one here. I think a lot of the things are similar. How do the IEC countries address this versus North America?
Good. Yeah, no, it's a good question. So in IEC land, they probably make more use of their version of arc resistant than we do in the U.S. Now it's different terminology, and obviously it's different standards, but the test requirements are virtually identical. With IEC for medium voltage, they call it IAC, internal arc classified, basically the same as arc resistant switchgear, and they use that in a lot of cases as kind of their baseline. We're starting to see more interest in mitigation in facilities around the world. In some cases, it's U.S. facilities that have or U.S. companies that have manufacturing facilities in other locations. But to a great extent, they've got access to the same type of solutions that we do. They can put in high resistance ground. They can do these thermal sensors to give you some avoidance solution kind of thing. They have relays that do the same stuff that our relays do. You can put maintenance switches on those as well. They may not have the optical arc flash sensing actually was developed in Europe and kind of came over to the U.S. rather than the other way around. So it's the low voltage circuit breakers with arc flash maintenance switches on them are probably not as prevalent or popular in the IEC market, but a lot of the rest of the solutions are you're going to find kind of the same solution set that we have. It's just that it may not be applied quite as often because they do make more reliance on their arc resistant gear.
Thank you, Tony. Please go to the next slide. We don't have much time for any more questions. I do want to go over a couple things real quick. In the chat, I put 2 links that are also on the screen. Again, EasyPower will put this webinar on demand to view, as well as provide a PDF copy of the presentation. We are on the cusp of releasing that arc flash mitigation guide that you kind of previewed a little bit in this presentation. And if you join our portal for engineers, designers, and specifiers, you'll be able to see that. Also, if you connect with me on LinkedIn, I try not to spam with a lot of posts on LinkedIn, but I do talk about webinars, design guides for engineers, and other miscellaneous important things. I also want to say questions. I know there are quite a few here we didn't get to answer fully. On our portal, we have a forum that is not manned by what I would call customer care, but manned by our consultant specialists. These are guys who are either engineers themselves or been working in the industry for years, working directly with engineers, and can answer electrical distribution questions. They are available on the portal via chat, email, and the forum that I've mentioned. So I highly recommend going there and answering any questions, get more detail. We will be providing a 3 to 5 part webinar series that's going to go into detail of all these solutions that I showed you in the table, as well as talk about some of the highlights in the beginning about choosing correctly and designing arc flash mitigation. Thank you, everybody. I appreciate it, and hope to see you in the future. Thank you.
Yeah, thanks.